Hi, folks. My name is Imran Qureshi. Together with Iman and Alvin today, I will be talking about model explanation and prediction exploration in Spark. We would love to get any feedback about this session, and so feel free to send that our way. So I will cover the introduction section. Why should you do prediction explanation? What are the current approaches? Why we felt those approaches did not meet our needs? And then I will turn it over to Iman, who's going to talk about the details of our approach. How did we implement that for GLM? How did we implement that for random forest? And then we will talk about the open source library we're making available if you wanted to use this in your own Spark implementations. Let's jump straight in. Before we go into the details, let's talk a little bit about Clarify Health so you kind of know who we are. We process over 11 billion healthcare claims today. That covers 150 million patients. That's over 40 terabytes of data. We have a lot of models that we train. Right now, that number is actually over 2,000. And then we have over 2,000 features that feed into those models. In terms of our infrastructure, it's all built on AWS and Spark. Right now, we can train 16 models for about 84 million patients in about 5 hours. In addition, the accuracy of our models is also in line with the industry standards. For example, we can predict mortality at a better rate than Elixhauser, which is one of our standard models in healthcare. And then we can also predict the total cost of a patient about the same accuracy as the healthcare industry. So talking about how we got started, right? We started with like everyone else, probably all of you guys. We took some features, we threw in a whole bunch of data, we tuned some hyperparameters, we chose some algorithms, and then we sort of turned the crank and out came predictions. And we were pretty happy. We just took them to various doctors and healthcare executives and life science companies, and we said, look at this. So what happened is probably what you've all experienced. People started questioning our models. Someone would say, how do I know your model is correct? Right? This comes up to a quick question. Other people started asking, well, why does Dr. Iman cost twice as much as Dr. Alvin? What is Dr. Iman doing differently? Other people asked, how much does age versus the diagnosis of the patient contribute to the prediction? Then people started asking what if questions. Well, what if Dr. Iman reduced his ER visits from 2 to 1? What would happen to the cost of his patients? The question about bias, of course, comes up, and people said, okay, show me that your model is not biased for race. And really, largely, when we took our models to doctors and we used them to tell doctor that they needed to do something differently, the reaction is what you would expect. If you've never done that, you should feel free to try and see what happens. So what we quickly learned was we really needed to explain our models more. Just showing a prediction, whether it was a total cost or mortality or any prediction, was not enough. So when we started imagining this, okay, what should that explanation look like? What should the exploration look like? We came up with a few requirements. So our first requirement was that we needed to be able to show the contribution of each feature in prediction units. So for example, if we said that patients over 65 add $300 to your average cost, then that has to be in dollars to match up with our prediction, which is in dollars in this case. The second requirement was that these feature contributions should add up. For example, if having patients over 65 adds $300 of cost and having a cancer diagnosis adds $400 of cost, then the inpatient cost should be the sum of these, or $700. Another major requirement was it had to work on any arbitrary subpopulation. So we can't define all the subpopulations of interest ahead of time, because in our application, users will go and they will create their own subpopulation to analyze. So it had to be something that would be done at runtime, not before that. And we needed to really work with GLM, generalized linear models, and random forest algorithms. Certainly linear models are really easy to explain, but for types of data we need to predict, they're not good enough. And as I mentioned before, we deal with very large volumes. So it had to be something that would scale for thousands of features on many millions of rows. And it also had to enable the what if analysis scenario. So for example, people want to ask the question, what if I reduced my ER visits by 10%? What would my total cost become? And lastly, it had to work in Spark. All our infrastructure is in Spark, and we did not want to build another infrastructure to handle that. So then we looked at what are the solutions that are available out there. So the first solution that's common is called Lime. And if you look at how it matches up with our requirements, it does show the contributions in prediction units, but the feature contributions do not add up in Lime. And it doesn't really allow you to work on an arbitrary subpopulation at runtime. The way it does work with GLM and random forest algorithms, but it works using a surrogate model, which is close but not exactly what your model is doing. It definitely does not scale. There is no good implementation in Spark right now, and the other implementations take a very, very long time. It does enable you to do what if analysis, but as I mentioned before, it does not work in Spark. The other option that's available out there is called SHAP. So this, again, does work in the prediction units, and the feature contributions do add up, but it's not designed to do this on an arbitrary subpopulation. You sort of have to do your SHAP analysis ahead of time before you can show that. It again uses a surrogate model, which is close, but not exactly what the existing model does. And it certainly doesn't allow you to do what if analyses. So let's take an example of what the end result looks like before Iman walks you through how we built it. So this is an example of the end result. So in this case, you're looking at a prediction explanation. And if you look at the top right, you can see the predicted average cost for this subpopulation was 14,581. So what actually made up that prediction? So if you look at on the left-hand side, or actually on the bottom, so we're showing relative cost compared to the whole training population right now in this view. So that's at 0. So then you look at in this population that I'm looking at compared to the whole population, their cost in the past 365 days is higher. So if you look on the left-hand side, we have a bug. Of course, it shows percentage instead of dollar amounts, but really it should be the cost in this subpopulation is $20,800, and the cost in the whole trading population was $19,800. So the cost in the past 365 days for this subpopulation is higher. So you can see that that adds $344 to the predicted cost in the next year. Similarly, if you look at the next row, it's talking about the patients in the percentage of patients in this subpopulation that are eligible for Medicare. You can see that it's a smaller percentage, 19% compared to the whole population of 22%. So what that does is that reduces your average inpatient cost by almost $70. So again, you can go down here and you can see the contribution of every single feature and how that feature is different from the whole population. And that's showing up on the left-hand side. And the right-hand side, those bars are showing the contribution of all of these features. So if you added up all these bars, you would get to 14,581, which is essentially the predicted cost. So this really allows our customers to understand exactly what the behavior of any subpopulation is compared to the whole population. It also helps them understand what the differences in features are contributing to the difference in the prediction. And this really helps them provide that visibility into the model. And we found that when we presented this to our customers, they really started to believe our predictions and our model. So at this point, I'm going to turn it over to Iman, who's going to walk you through how we implemented this for both GLM and Random Forest, and then talk a little bit about our open source library that's available if you wanted to use this.
Hi, Iman Haji here, and I'm gonna walk you through our methodology for explanation of random forests and GLMs. Let's start with a GLM explanation. So the very simple case of GLM, so you see the equation here. The prediction for a GLM is a nonlinearity denoted by H applied on the sum of feature weights multiplied by their values. So a very simple case of this is the linear regression, where this nonlinearity H is actually identity. In that case, if we call beta or weight of each feature multiplied by its own value as the linear contribution of a feature, the prediction for a linear regression is the sum of linear contributions of features plus the intercept. So in that case, explanation is very straightforward because the contribution of each feature to the overall outcome is basically its linear contribution, or the feature weight multiplied by its value. But then things get more complicated once the nonlinearity kicks in. So if we have to pass the sum through a nonlinearity such as a sigmoid, then explanation becomes complicated because we have a bunch of positive and bunch of negative contributors, and then the overall overall prediction comes out of a nonlinearity. How do we break down this overall output within and among the contributing features? So the way we do that is very briefly, we pool the features into two bins. One is positive contributors and one is negative contributors. And then we linearize their contribution to the overall outcome around the point of intercept. Now, I'm not gonna get into the mathematical details. We're working on a paper and hopefully it'll be published soon and you can refer to that. What I'm gonna do instead is let's look at a couple of examples and see how our algorithm deals with prediction explanation. So on the top, you have the identity link, which refers to the simple linear regression. And in the bottom, we have the sigmoid activation, which results in the popular logistic regression. So both linear regression and logistic regression are special cases for generalized linear models, or GLMs. So on the top left, you have feature one, feature two, and intercept columns. And for feature one and feature two, we have the linear contribution. So what is put there is a feature weight multiplied by a feature value. And as you can see, for the top table, our algorithm, what it spits out as feature contributions are simply the linear contributions. So the columns that you see inside the red rectangle mimic what you see, the three columns that you have on the left, because we're dealing with linear regression. And on the right, you see the prediction, which is the sum of linear contributions. The rightmost column is the prediction column, and the contrib sum is the sum of the contributions that are generated by our algorithm inside the red rectangle. Now, things get more complicated if we go to the second table. So what we have there is, again, we have the linear contributions on the left, but this time, the sum of these linear contribution gets passed through a sigmoid function because this is logistic regression. So for example, for row number 0, we have feature 1 as 0, feature 2 as 0, and intercept is equal to 1. If we sum them up, it's going to be 1, pass it through the sigmoid, and we have 0.73, as you can see on the right. Now, the algorithm correctly says, all right, feature 1 was 0, so it's not contributing to the linear sum, so it shouldn't be contributing to the overall outcome. So the same goes with feature 2, and the overall contribution of the intercept is going to be 0.73 because the sum of these contributions should add up to the prediction. Now, the second row, which is row number 1 here, the feature linear contribution of feature 1 is 1. For feature 2, it's -1, and intercept is, again, 1. So the sum is still 1, because 1 plus -1 plus 1 is still 1. Pass it through the sigmoid, and the outcome is still 0.73. But this time, the algorithm correctly identifies that, all right, we have two features that are non-zero. One has a positive contribution, one has a negative contribution, and it allocates contribution for them to the overall outcome. So they have 0.19 and -0.19, and again, intercept contribution is 0.73. So the total of these three contributions, again, adds up to 0.73. Now, you can look at rows 2 and 3 by yourself. I would like to compare row number 1 with row number 4. So as you can see, the linear contribution of feature 1 in row number 1 is 1, and in row number 4 is 2. And for feature 2, again, the linear contribution is doubled. And in the red rectangle, you see the contributions determined by our algorithm. As you can see, the contributions are scaled as well. They're not exactly doubled because we have a nonlinearity here, but good news is the algorithm first identifies negative and positive contributors and sort of preserves the scaling as best as possible given the nonlinearity. Let's move on to random forest and how we explain a random forest. So if you want to explain a random forest, or if you want to explain a forest, you better know how to explain a tree. So let's start by a decision tree. So this simple example is we have a model, let's say, to predict a simple predictor of a house price. Let's say the house price is estimated as 400,000 multiplied by if the square footage is greater than 1,000, plus 300,000 multiplied by if the bedroom count is greater than 2, plus 200,000 multiplied by if the house is built fairly recently, the age is under 15, plus an intercept of 100. Now, if we want to train a regressor tree to return these values, it'll look something like this. So the first branch is square footage, and then bedroom count and house age. And you can see we have 3 features, binary features. We have 8 possible outcomes, and the tree looks like this. So at the time, we wanted to explain, first we wanted to use random forests or tree ensembles in general, and then be able to explain them. We looked around and we found a solution out there that does something like this. First, we have to calculate the average of the leaves associated with each node at the node. So for the first node, where we see square footage, the root node, let's say, the average value of all leaves is the average of all outcomes, all of the 8 outcomes, and it's 550,000. Then let's say we go to the upper branch, we can see that for that node, we have to average the top 4 outcomes, which are 1,800,000, 700,000, and 500,000. We do that, we get 750. And again, for the upper node, if we go forward, we have 900,000, which is the average of 1,800,000. Now, the algorithm said that you consider the average at root as the contribution of intercept. So 550,000 is going to be the contribution of the intercept. And now let's consider the case that we want to go, we want to have an estimation for a house that has greater than 1,000 square footage, bigger, more than 2 bedrooms, and the age is less than 15. So we're going to go with the uppermost branch. And the prediction is 1 million. So we start from the root node, which is the contribution of intercept, 550,000. Then if we go up again, we have to add another 200,000 to get to the next average, which is 750. So 750 minus 550 is 200. So the contribution of the first feature, which is square footage, will be 200,000. And again, we go forward. If the bedroom count is greater than 2, 750 becomes 900. So we have another 150 added. And again, if we go forward, if the house age is under 15, we have another 100,000. So let's put all of this together. On the top, we have the original model that we wanted to emulate using the decision tree. And on the bottom, we see the contributions. There is a problem here. And the contribution of square footage was supposed to be 400,000, but now we estimated it as 200. The same goes with bedroom count, house age, and intercept. It was supposed to be 100, but these numbers don't match. And that's where we had to design our own prediction explainer, because what we wanted was a prediction explainer for random forests that matched a linear regression and matched our prediction explainer for GLM that I just explained to you. So here's how we do it this time that matches linear regression. So for the contribution of intercept, we set all feature values to 0. So we call this the exclusion path of the roots node. And it's going to be denoted, it's going to be shown by the red path that you see here. So the outcome of the prediction of this red path is 100,000. So we consider that the contribution of the intercept. So at each node on the graph, we have an exclusion path, meaning the remaining features are going to be set to 0. And we have an inclusion path, meaning the value of the current feature is going to be set to its actual value for that prediction, and the remaining features are going to stay as 0. So for example, for the first feature, square footage, we see that the inclusion path is the green path here, and the red path is the exclusion path at that node. So the difference between the outcome of the inclusion and exclusion paths is going to be 500 minus 100 is going to be 400,000. So that's going to be the contribution of square footage. Now we go forward in the tree. We fix the square footage as what it was. And then for the next feature, we do the inclusion and exclusion paths again. So bedroom count, if it wants to be greater than 2, for this prediction that we were talking about, it is. So the inclusion path is that feature is going to be set to 1, and the rest of the remaining features are going to be 0. So again, the contribution of bedroom count is going to be 800 minus 500, which is 300,000. And we do the same thing for the remaining nodes. The next one is house age, 1 million minus 800,000. It's going to be 200,000. So that's the contribution of the last one. So if we put all of these together, what do we have? Looking up again, we have the original model. And now in the bottom, we see the contribution of intercept is 100,000, and the contributions line up nicely. So that's what we wanted. So we have a prediction explainer for decision trees that matches our interpretation or our expression using linear regression or GLMs. All right, so we explained decision trees, and once you can explain a decision tree, any ensembling of the trees are explainable. And we've implemented it for random forests using some simplifications as well to make it faster. But what we have here as these are the benefits of our approach. We have the GLM and random forest explainer. They're distributed. Implementation is available in Spark, and we have open sourced them. I'm going to show you how you can access them. They're scalable, and they're also applicable for Python and Scala. So let's talk about our libraries. Our chief data scientist, Alvin Henrik, has implemented these and has done a great job of optimizing the implementation. And you can see the README files are also available. Please refer to them. There's a lot of information there helping you to use them. But simply what this is a drag and drop now. You have the transformers implemented. What you need to define, this is the GLM explainer. You have to define your coefficients that you have used that you get from the model you have trained. You have your predictions, of course, and you give the prediction explainer transformer the family that you use for your GLM, Tweedy, Gamma, Poisson, or whatever it is, the link power, the variance power, these are the attributes of GLM. And then you define if you want the prediction explainer to come out as a nested array column, a column of nested arrays, or you want separate columns, and a bunch of other attributes that you can set. So please refer to the README file. There's detailed explanation of those. And at the end of the day, it's just a transformation. You give it the original data frame, and then it creates an additional column, which is the prediction explainer column, feature contributions column, and you have your prediction explainer there. And the same for random forest explainer. You have to give it the, we call it the coefficients here. They're actually the feature importances that you extract from the random forest. And you have to also give it the random forest model. So you have to define the model path, because as I said, for each node, we have to make the prediction for the inclusion minus exclusion path. So we have two predictions at each node. So we need access to the original model. And it does this very quickly. So just to give you an example, if we wanted to, let's say, explain hundreds of millions of rows that we do very often at Clarify, 100 million rows, let's say, that would take, if we want to use something like Shapley, it would take us months or years to do that. But in this fashion, that could be done in 30 minutes to an hour. So which is hugely time saving. And this is our the URL for our GitHub repository. Please feel free to download, and we would love to see your contributions to that and your comments to that. They're ready to integrate. Just drag and drop the transformers into your projects, into your pipelines, and instructions are on the README files. Currently, we only have support for generalized linear models and random forests. But as I said, any ensemble tree is within reach. We just haven't done it. These are fairly recent developments. So if you want something, or if you have suggestions for additions, please let us know. And that's it. We'll be glad to take your questions.